Pleasure to be here. I hope you've had good talks today, and there are more exciting things to happen. I heard that the challenges have started really well. That there have been several teams that completed everything already. So I think the hackathon will be really cool next week. So my talk is called "What Co-Design Can Do for You," and that has something to do with my job here at IQM, right? It says tech lead for co-design. So my idea was here that co-design is something that we do at IQM. We build co-design quantum computers. So I'll tell you what co-design is, and from there I'll try to extract some tips for you guys for the hackathon on the sort of things that will be helpful for you, the sort of things that will make your code run better, that will give you better results in your hackathon projects. And at the end, if we have time, then I have a little request for you guys as well to give me some ideas for what to do with my co-design quantum computers. So the talk is very simple today, right? It's just 15 minutes. So I'll just tell you what is co-design, and then I'll give you an example. And we'll spend most of the time here on the example of co-design quantum computing. Like what can it look like? So we'll start with co-design. And co-design is an old design philosophy where for us in quantum computing, what we're looking at IQM is that it lives here in this intersection of use case, of the quantum hardware, and of the software, so the quantum algorithms that we're running to solve the use case. So this means that we're looking at things, we want to optimize the whole system, considering the use case, so we want to pick a problem that fits quantum computers, in particular noisy quantum computers, and the sort of things that we can build. And we want to look at the hardware and see how can we fit the hardware best to this use case. And we also want to have the algorithms which are useful for NISQ, if such exists, and that solve the problem particularly well. Now, looking at this sort of diagram, this sort of Venn diagram, you can draw arrows everywhere, and everything depends on everything. So it's difficult to analyze and difficult to get a grasp of what's going on. So one way we like to think about that at IQM is to think about our co-design building blocks. Right? At IQM, we build superconducting quantum computers. So we want to have some building blocks that we put together to do that. And in standard quantum computing, you would start off with qubits. You would pick your favorite qubit, and you would then connect that typically on a square lattice in order to run error correction on that. And then you would do single and two qubit gates, and you pick some two qubit gate because you know that if you have access to arbitrary single qubit gates and some two qubit gate, then you're good. It's universal already. You can do anything you like. But then in practice, there's a question of, okay, what are the best gates you could do? What are the best way to connect your device? And should I even be using qubits? And as physicists, we of course know that there is this much larger toolbox with many more building blocks out there. So we could use qubits, we could use qudits, which are n-level systems, d-level systems. So qtrits or qquads, I think is a word, or so forth. Or we could even do resonators. So in some sense, infinite dimensional objects. And once we've picked this basic element, computational element, we can then connect them in some topology. This could be square, could be a hexagon, could be something irregular, could be a star, could be many things, whatever fits the problem. And finally, we can look at how do we use the device. Do we do single and two qubit gates with whatever two qubit gate that happens to be our favorite for some reason? Or we could do multiple two qubit gate types. Combining two different types of gates can actually be really powerful. Or we could even do analog simulation with a device, or hybrid digital analog computing. So there are many things we could do here. And this is where we'll now start looking at this example. And you can see that was sort of hardware specific. In this example, I talk more about algorithms and applications a bit. So don't worry, this will be practical for the hackathon. So the use case I talk about here is developing safe and efficient contrast agents for MRI. So there's some patients in hospitals who will need frequent MRI scans to track, for example, tumors. And those patients, they will often need a contrast agent, so magnetized material that gets injected into the patient to give a clearer signal in the MRI. Typically, this contrast agent is gadolinium-based, and in the medical jargon, it has a low biocompatibility. So it's a poison. You don't want to put that into patients too much. So that starts to restrict your capability to do MRIs frequently. So there's a proposal that we could make a safe and efficient contrast agent out of nanodiamonds. So diamonds, they're inert. They are kind of, it's a carbon lattice. It's not really reacting with stuff. So it has high biocompatibility, but we need to magnetize it. And just sticking it in the magnetic field won't cut it. So there's a proposal that if we spray these diamonds with nitrogen, then we can create NV centers where some of these carbon nuclei get replaced by a nitrogen nucleus, and therefore a vacancy next to it because nitrogen can only have 3 bonds. And this here is actually a qubit. And this can be addressed, it can be addressed with lasers and microwave light. And now by driving this qubit, we can actually polarize it, we can magnetize the NV, and we can transfer the magnetization into the nuclear spins of the carbon-13s. So mathematically, what we're looking at is a problem where we have an NV, and it's interacting with some carbon-13 nuclei through this NV-N nucleus coupling. And then furthermore, we might have some interactions between the nuclei, some internuclear forces. And then we have a microwave drive on the NV center. And the problem that we now want to move into a quantum computer, so superconducting quantum computer in this case, is simulating this system under various driving protocols, because there are many driving protocols there could be in order to optimize this polarization transfer. And doing this experimentally can be really slow and tedious. And so we want to simulate this process on a quantum computer. And what does the whole procedure look like is that we would initialize the NV center in the 1 state or the plus state, depends a bit on the driving scheme. We would then allow time to pass, so we would simulate time and transfer this polarization. Then we would reinitialize the NV, transfer, reinitialize, transfer, reinitialize, transfer, etc. And what we would be doing in the quantum computer is that for each of these polarization transfers, we would be checking this sort of plot where we'll look at how much polarization transfers over to the nuclei. And here we're scanning across the frequency range of the driving to see where the peaks are. And these peaks tell us at what frequency the polarization transfers very well, because if there's no driving, the polarization doesn't transfer, but only at certain frequencies it transfers. And this is where we start to see what is nice about this problem for quantum computers, is that all of these terms, so we have the Hamiltonian for the NV and the Hamiltonian for the nuclei, these are spin Hamiltonians. These are spins already. And so are qubits. Qubits have the same operators as spins. So we're not doing mappings like if we're simulating the electronic structure problem in chemistry, where we need to map fermionic operators to spin operators. The problem is already natively in the language of quantum computing. So that's a really nice plus. And then what will happen here is these are the curves without noise. If we add some noise into that's coming later. Add some noise into our simulation, then these curves will flatten. But as the curves flatten, that's all right, because we care about where is the central frequency, where is the peak. We don't care about the value of the peak per se, because if we underestimate the value of the peak, that means we just transfer too many cycles. So here we're scanning over the cycles, you see the peaks growing. And if the real peaks are higher than what we predicted, that's not a problem. We just did it too many times, and you will saturate anyway. So the problem has some sort of inherent noise robustness within it. So now, how does it look on a quantum computer? On a quantum computer, we'll have the same sort of structure where we have time evolution, we have resets, and time evolution again. Here is an example, we're using trotterized evolution because it gives nice circuits, but that's not fundamental here. And in the beginning, we have some initial state preparation where we initialize the NV in the polarized state and the nuclei in a maximally mixed state, which simulates room temperature very well. And within this trotter evolution, the structure of the circuit is that the NV has gates to all the nuclei, like this. And then there could also be internuclear forces in between here. So we could have some 2-qubit gates in between the nuclei as well. But the dominant one is always going to be from NV to nuclei. So now we can look at two different implementations of this, right? So we can implement this on your typical square grid quantum computer, or we could look at implementing this on a star topology, like on the left. And when we do this, we're going to have to start putting in some swap gates, because these topologies don't have the same, they don't have the all-to-all connectivity of the full problem. But the star, of course, has the one-to-all connectivity of the simplified problem. So what we're seeing is that if we look at a non-interacting case where we have no internuclear interactions, then we will have no swaps on the star. So we will save 100% of the swaps that we introduce on the square grid. While if we do the fully interacting case, the all-to-all interacting case, then we will have some swaps. We will need to do some swaps on the star as well. But already at 20 or so qubits, we will be saving 90% of the swaps. And swaps are kind of bad gates. You don't want to do them when it's absolutely necessary, because swaps are typically 3 C0 gates, and so it has the error of 3 2-qubit gates. And that's the thing that really limits you. So by going into a star topology, or in general in a topology which fits the structure of your problem, you can generate a lot less of this waste, right? Here, the square grid generates 10 times more of these wasteful gates than a star topology. And so here I wanted to show this, that we've done the simulation. So this is not on real hardware yet, but this is the ideal curve, the red curve, and it gets flattened out when we add noise into the simulation. But as it gets flattened, that's okay, because as long as we can tell apart where is the center of this peak, then we can extract the information. That's the important information we want. So in some sense, in solving this problem, when we're looking for these peaks, we're at the same time doing error mitigation. You can think of fitting a curve on this as an error mitigation technique. So solving the problem has this inbuilt error mitigation in this case. So now I showed you the number of swaps saved, but what does it mean in practice? In practice here, we're looking now at the average error in the peak frequency. So we're looking at where is this peak located. And of course, the ideal case is 0. So if there's no noise, then we will have no error. But if we're doing this on a square grid, we see the red line. And if we're doing this on the CoDesign chip, the star topology, we're seeing the blue line, and we're scanning across the 2-qubit gate error. And state-of-the-art 2-qubit gate error are somewhere around here, 10 to the minus 3, or 3 nines of fidelity. And there we see that we get a factor 3 in improved accuracy, quite a bit. But we can also look at it the other way and say that actually with 2 nines of fidelity, or 99% fidelity gates, we get the same accuracy on the star chip that would require 4 nines of fidelity on the square grid. So this is the sort of thing, this is how we can make experimentalists' lives easier by putting our problem on the right part of the chip, or on the right type of chip. And so we don't have to demand as much fidelity from the gates. That's the really difficult thing to do. And now we'll skip the bonus part, since I'm already running out of time. So we'll move to the conclusions. So everything I was talking about here today is in this paper and published in Physical Review Research a couple months ago, or on the archive. And take-home messages here, for one is that the swap gate count really matters. So when you're to use this to choose the device you're running your thing on in the hackathon, if you're running some algorithm and it has some certain connectivity on the algorithm, then try to find something that matches that as nicely as possible on the hardware. And when you think about what you want to do in the hackathon, think about choosing something which is noise robust and which might have some error mitigation built in, so that when you're solving the problem, you're at the same time allows you to fit a curve in some way, for example, that allows you to be less sensitive to noise. So there are these sorts of problems out there. And finally, I am here to advertise. So despite the news we've heard about the quantum community, that the job market is turbulent, we are hiring across all of our locations. Most recent locations in Singapore, where I'm just going next week to go establish some collaborations. So have a look at our careers website, and if you don't find anything interesting there, you can message me. Everything is always possible. And finally, we are also hosting the SQA conference, the Superconducting Qubits and Algorithms conference in August in Munich. The first one was last year. It was really, really, really great conference where we were really at this interface of quantum algorithms and superconducting quantum computers, and how do we make them play nice together? And this was really, really great. So if you have a chance to come to Munich at the end of August, I really recommend this. Abstract submissions are open right now, and they'll stay open until end of April. And I can only recommend this. So thank you very much.
Thank you so much, Hermanni. This interface between the sort of abstract algorithms and the concrete sort of implementation hardware is so rich and interesting. It seems like a great place to be working. It sounds like you've had a chance to live and visit like many places in your career so far in quantum. Is that right?
That's right. Yeah, I was doing my PhD in Singapore. So I'm originally here from Finland, and then I was studying at some point in Hong Kong, and then PhD in Singapore for 5 years. And then somehow I found out that IQM was founded about 2 kilometers from where I grew up, and found my dream job here. So, yeah.
It's awesome. Yeah. I did have a couple of questions for you. Just to remind folks in the Twitch stream that if you stay active in the chat, you could be eligible for a giveaway shortly. But before we get to that, I wanted to know, where was your favorite place to live so far? And, good question, right?
Good question. I really love staying in Hong Kong back in the early 2010s. I think it's quite a different place today, but I really love that. So such an amazing city and amazing food.
Yeah, I visited many years ago, and it was fantastic. We also have some questions from the audience. We had quite a bit of speculation as to what IQM stands for. We had Institute for Quantum Memes was one proposal, or International Quantum Magicians. What does it actually stand for?
I like these. So I like the speculation. That's all I'm doing as well. The story goes that the founder of the company, Mikko Möttönen, knows what it stands for. He went to pitch the idea to investors. They never asked. And after that, he's kept it a secret.
Wow. Okay. I had no idea that's what was coming. Okay.
Yep. And my strategy is to try to get him into the lab, stick him in the fridge, cool him down to millikelvin, and run a Grover search on him.
Ooh, okay. I mean, that sounds like a really practical approach. I love it. On a slightly more serious note, we also had a question from IoTi Solutions asking, how does IQM overcome the difficulty of entanglement with Diamond NV?
Overcome the difficulty, right? So we're not actually using Diamond NVs. That's the system we're simulating. So I'm not sure if that is answering the question, but so we're not trying to use that as our computational platform.
Right. Yeah. Thank you for that. The other question we had was for a master's in quantum, which country do you recommend, Finland or Singapore?
Ooh,
if you were choosing.
Okay. Let's say it depends a little bit. I haven't studied in Finland ever. I can't really tell about that. But from what I'm seeing from the guys coming here from Aalto University, I mean, they're very strong in really the sort of superconducting stuff on superconducting circuits, quantum computers, really the practical side and the experimental side, and really this sort of interface thing of, okay, how do we use these devices? Whereas in Singapore, I see a lot more of this more fundamental theory research of entanglement theory and fundamentals of quantum computer science and that sort of thing. There's also the experimental side, especially in cold atoms. But for me as a theorist, I think for me, Singapore was a much better place.
Awesome. Well, thank you for answering that. There's a few more questions in the chat. I think you're going to be on Discord for answering some questions afterwards. If folks have more follow-ups, they can join you there. So thank you for that. And do folks check out the job board at QHack.ai to see what possibilities there are at IQM. And thank you, Hermanni. We'll say goodbye to you now, but not goodbye to the folks in the Twitch stream.
Thank you.